Okay. So in the last class, we started with analyzing parallel adders, right? So we designed an adder cum subtractor also in the last class. These are combinational circuits. Why we are using or why we are emphasizing a lot on full adders is because all arithmetic operation inside computer will be performed by full adders only. If you want to perform multiplication, then it is again by full adder. You will do successive addition to perform multiplication. If you want to perform division, then you will do a shift method. So that you must be knowing you if you have done C programming. So which means adder is a more important component as far as computers are concerned or digital equipments are concerned. Hence, we emphasized a lot on adders, that is the two different bit adders, 4-bit adder, 8-bit adder, 16-bit, 32, 64-bit adders. Then we, towards the end of the class, we touched upon what is called as a magnitude comparator. The magnitude comparator we touched upon was a single bit magnitude comparator, which means that the input variables here, x and y, they are all single bits. X and Y, they are all single bits. So hence these four input combinations were there. So based on the inputs we compared. Now what if these are multi-bit variables? Meaning, say for example, if X can take 1001, right? So 4-bit comparator, and Y can take 0010, right? So these are multi-bit comparators. So practically if you look, 1-bit comparator is of no use, but multi-bit comparators are useful. Now, how do you design this? So what is the problem statement here? The problem statement here is design a multi-bit comparator. Let the multi-bit be, say, 4-bit. Now, let me take a very simple example. If, say, for example, x is equal to the same thing, I'm rewriting it. X is 1001 and y is 0010. If I want to compare these two bits, we all know that x and y are 4-bit variables. How do you do it? If you use K-map, then it will be very, very lengthy. Why it will be lengthy? Because here x here will be represented as x3, x2, x1, x0. Similarly, y will be represented as y3, y2, y1 and y0. So there are 8 different variables here and 2 power 8 combinations will be there, and its corresponding output you have to map, and creating a K-map again, it's a problem. So again, we have to think logically, how do we implement this 4-bit comparator? Simple logic that you can see here is you will have to compare the most significant bit. Here the most significant bit is 1 and here the most significant bit is 0. So from these two comparison itself, you can say that x is greater than y. If, say for example, my x value is 1001 and my y value is 1100. Here, both my MSB bits are 1 here and 1 here. So your logic will not work if you are comparing the MSB. So what you should do? If both my MSBs are equal, then what I do is I move on to my next most significant bit comparison, which means that I will compare this 0 and this 1 now. And from here itself, I can identify that y is greater than x here because 1 corresponding to y is greater than 0 corresponding to x. What if I have 1001 and y as 1000. Here again the process will get repeated. That is, first this one will be compared, the MSB bit will be compared. If they are equal, then the next bit will be compared. If again both these zeros are same, then you proceed further with the next significant bit. Likewise, you continue till all the values are being checked. Okay, so this is the logic that we are going to use for this multi-bit comparator. So there are the same thing, whatever I have described now has been written in statements here. Let us quickly go through it. So the simple method will be is, if you want to compare, then first compare the MSB bits, most significant bits. If they are not equal, then no need to compare other bits. So whichever MSB is greater, then that particular number will be the greatest one, as in the first case that I did. If x3 is greater, then no need to compare the rest of the bits. So now you will have to continue this until the number is found to be greater than the other number, or all other bits are checked and the numbers are found to be equal. If you keep on continue to check all the other bits and if they are same, if this is also 1001 and this is also 1001, then you keep on checking till the LSB bit, least significant bit, then you conclude that both are same. Now, okay, it is very nice to say it in words, right? But how do you implement it digitally? How do you implement it digitally is, now let us take an example now. We are going to do a 4-bit magnitude comparator. Again, what is the problem statement here? Problem statement here is 4-bit magnitude comparator. Immediately what we will do, we will assign our input and output variables. So what we are going to do is, let A and B be the two 4-bit input variables. And what are the output variables here? Output signals here. My output signals will be either, my first signal will be either it will be A is greater than B. Second is A less than B. And third is A equal to B. So these are the three possible output signals. And what are the input signals? A and B. Please note that A is a 4-bit number and B is also a 4-bit number. So let us assume that the 4-bit A corresponds to A3, A2, A1, A0, and B corresponds to B3, B2, B1, B0. Obviously, it is very difficult to use a truth table approach, right? Because there will be 8 different variables and total number of combinations that you might have to do is 2 power 8 different combinations. So better not to try using a truth table. However, if you want to waste your time, then you can definitely try the truth table method. Okay. Now, what is the procedure? How do we check? First, let us check for A equal to B because it's slightly easier. What do you do? If I want to check A equal to B, please keep all these variables in mind because if I scroll up and down, then you might lose track. So better to keep in mind the variables A3, A2, A1, A0 corresponds to A and B3, B2, B1, B0 corresponds to B. Now, if I want to check A equal to 0, then simply what I should do is I must compare A3 with B3, A2 with B2, A1 with B1 and A0 to B0, right? So how do you, which gate will you use to compare the equality? Which gate corresponds to an equality function? It is XNOR gate corresponds to an equality function. Why XNOR gate? Because when both the inputs are same, or both the inputs are same, then your output will be one only across XNOR gate. Across XOR gate, when both the inputs are same, they will be 0. Your output will be 0. So hence it is not XOR gate here. Uh, it is XNOR gate. So please keep on recalling the previous terms. We use XOR gate for what? We use XOR gate for odd functions. When I say odd function, it means that it is used as a parity checker. Okay, So all these things must immediately come to your mind whenever we are introducing new gates for a particular function. Okay, now back to the topic. So how do you implement this? How do you compare these bits A3 equal to B3? You can simply use an XNOR gate. Whenever your A3 is whether it is 1, both are 1, then your XNOR output will be 1. If both are 0, then your output will be 1 if you are using an XNOR gate. So which means that mathematically or as per the Boolean algebra, we can simply write that my output variable across my XNOR gate X, let me write it for one variable X, will be equal to AB plus A bar B bar. Am I right? Because what is the truth table function of an XNOR gate? 0 0 0 1 1 0 1 1. So when both the inputs are same, it will be 1 0 0 1. So how do you write the equation for this? You will write the equation for this as A bar B bar corresponding to this 0 0 plus AB corresponding to this 1 1. Okay, similarly we have written here it is AB plus A bar B bar. Now since we are having a suffix here for each bits, that is A3 B3, A2 B2, A1 B1, A0 B0, we must introduce some suffix I where I corresponds to 0, 1, 2, 3, the number of bits that we are having. So we are comparing, if X is 0, then we are comparing A0 B0 with A0 bar B0 bar. Okay, so that is how. So simply we can write this simple Boolean expression where Xi will always be equal to 1 whenever both the inputs are equal. When they are 1 and 1 or when they are 0 and 0, you will have an output triggered to 1, right? When you will have an output triggered to 1. Okay, now have we completed this? Please note that this xi means I will have x0 which compares a0 and b0. I will have x1 when it compares a1 and b1. Likewise, I will have x2, I will have x3 after comparing all these individual bits. Is the job done? Now, when will I conclude that my a is equal to b? I will conclude that my a is equal to b only my AND operation of x0 dot x1 dot x2 dot x3 is equal to 1, because when a0 b0 are same, I will get 1 here. When this is 1, I will get 1 here. When this is 0 and if this is 1, meaning when x2 is equal to 0 means what? One of the bits are not same. So only if all these combinations are equal to 1, I can conclude that my A is equal to B. So that is what is written here. So for equality, that is A equal to B, all xi variables must be equal to 1. This dictates an AND operation for all the variables x3, x2, x1, x0. Okay, uh, so this is for a 4-bit case. If you want to extend this to an 8-bit case, simple, it is x7 dot x6 dot x5 and so on till x0. Right? So it is easy to implement an equality gate. Now, before, okay, so I thought I'll implement this in a circuit gate level logic. Okay, we will look at the next operation, that is a greater than b or a less than b. We have already discussed the logic of identifying a greater than b or a less than b. What is the logic? We first simply have to check our most significant bits, MSB bits. So yeah, okay, all right. So again, the same thing that I have said so far. If two digits are equal, then we compare the next lower significant. Okay. If we compare the relative magnitudes of a pair of significant bits starting from the MSB, then you have to keep on continuing that. That is what is written again and again here. So this comparison continues unless a pair of unequal digits are reached. So if say for example your corresponding digit is a equal to 1 and b equal to 0, we conclude that a greater than b. If a is 0 and b is equal to 1, then we conclude that a is less than b. Now how are we going to implement it? Now when we say a greater than b, when we say a greater than b, just a minute. Okay, let us, and we are looking at 4-bit variable. We are looking at 4-bit variable. So when I say 4-bit variable, we have A3, A2, A1, and A0. Similarly, we have B3, B2, B1, and B0. Now, if you want to compare A and B, if you want A greater than B, then what we do? That is A3 must be 1 and B3 must be 0. Meaning that A3 B3 bar must be equal to, if this is the condition that you have A3 B3 bar, then you will have A3 greater than B. Will it suffice? It will not suffice. Why? Because what if A3 is 1 and B3 is also 1? Then if A3 is 1 and B3 is 1 means this becomes 0. So the whole term will be 0. So A greater than 1 will not be triggered. It will not be triggered. So then what you have to do? You have to check the next bit. How do you check the next bit? Obviously, you will have to check the next bit. Okay, I have, oh, everything has come. Oh, okay, I thought I'll hide part by part. Okay, all right. So now, so we have compared the MSB bit. We have compared the MSB bit. Now, if MSB is equal, then what does it mean? Don't look at this particular part. I'll come back to this. If MSB is equal, then I have to check A2 B2 bar. If A2 B2 bar is also, if the second bit is also equal, then I will check this one, which is A1 B1 bar. If this is also same, then I will check this. What about this particular logic? Why should I include X3? Meaning that this must get activated. This must be, that is, these sequences must get activated only if this is A3 and B3 are equal. Am I right? Which means that if I am looking at A2 and B2, first I must check whether my X3 here is equal to 1 or not. If X3 is not equal to 1, it means that my decision is already taken based on my MSB bits. So since A3 and B3 are equal, then I move on to my next bit. Only then this minterm will get activated. And when will this minterm A1 B1 will get activated? Only if X3 is equal to 1 and X2 is also equal to 1, which means that these two variables must be equal to 1. Hence, you have X3, X2 here. Similarly, if I want to check the last one, then I have to first check my MSB, that is X3 equal to 1, X2 equal to 1, and X1 equal to 1. Okay, so that is what is written here. That is, this X3 corresponds to X3 equal to 1 only if A3 and B3 are same. Okay, any doubt here? Okay, great. Now, similarly, in case if you want me to expand further this particular part. Okay. Now this one checks A3 and B3. Okay, so just a detailed explanation for A3 and B3 bar. If we want to check A3 and B3, let us have what are the possible combinations of A3 and B3. I have 0 0 combination, 1 1 combination, 0 1 and 1 0 combination. So here A3 and B3 are same. So A3 B3 will not get triggered. A3 dot B3. Okay, so this is an AND operation here. So 0 dot 1 will be 0. 1 dot 0, right? Because for will also be 0. 0 dot 0 is again 0. 1 dot 1 will be 1 here. So A3 dot B3 will get triggered only when your A3 is 1 and B3 is 0. Likewise, anybody, can you get me the expression for A less than B? Let me understand, let me get whether you got the logic or not. The logic is very much similar. I have to check A less than B now. So just unmute yourself and get me the answer. That is, I need a Boolean expression here for comparing A less than B. Anybody, please? Please unmute and say. Please be quicker. Anybody? Anybody in the class? Some response? If you don't know, at least a thumbs down response. Simple logic, same logic. I compared A greater than B here. A3 bar with, yeah, correct, Deepika. You could have unmuted yourself and said, yeah, correct. So as Deepika said, the answer is A3 bar B3. Yeah. And then what will be the next bit? Next bit will be again, because if A3 and B3 are same, then again I have to compare, use this equal bit, right? A3 dot A2 bar B2 plus X3 X2 dot A1 bar B1 plus X3 X2 X1 A0 bar B0. Okay, so this is how you compare A less than B. Okay, now let us implement the same using digital circuit. That is, let us implement these three equations using the digital gates. So remember the three equations. In fact, this is our last equation. So what are our equations that we need to implement? We need to implement this equation as 1. We need to implement this as second equation. So these are the two equations for equalities, and the third and fourth one, right? So this is third and next one is fourth. So if you implement this, I hope you could recall these equations, because I have to move on to the next slide. Yeah. So this is how the circuit gets implemented. I mean, at the first look, you will get really scared. So don't worry about it. First, what are the equations we have? We have xi equal to ai bi plus ai bar bi bar, right? So and my x a equal to b will be equal to a equal to b. For this, I will have x3, x2, x1, x0 added together. Okay. Now look here. This is my a equal to b. I have added x0, right? And I have added, let me highlight that. I have added x0. I have added x1 here. I have added x2 here, right? It comes here. Okay. And then I have added this one. What is this? Just to track the line. This is nothing but your x3, right? So x3 comes here, 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 and then through this green line. Okay. So my A equal to B is implemented. Any doubt in A equal to B implementation? Anybody? I expect a question here because okay, nobody has identified. This can be implemented using XNOR, right? XNOR, right? So it's nothing but this is nothing but a complement of this is XNOR, a complement of XOR gate. So we have an XOR gate and its complement. That's what is written here. So if you have a complement of this, so what is the complement of this? This is AI BI bar plus AI BI. So AI bar BI will be the expression and the whole complement, which means that an XOR gates complement. Okay, so that's why you see here what is the input that you are getting here across these lines. These lines, okay, let us look here. So what is the input you are getting? You are getting A3 bar B3 plus A3 B3 bar, which is nothing but input of your XOR gate. So you pass it on to an XOR and then this particular bubble will take care of the complement. Okay, so instead of implementing BI plus AI bar BI bar, the complemented form has been implemented here. Why the complemented form has been implemented here? Because in A greater than B or less than B, we are using A3 B3 bar, A2 B2 bar, A1 B1 bar, and A0 B0 bar. Hence we are implementing this way. Okay. So you see here it is A3 knotted A3 bar you get, B3 knotted B3 bar. So and of this A3 bar B3 and of this one it is A3 B3 bar and the XOR of that and a complement of that, you will get this one will be equal to A3 B3 plus A3 bar B3 bar. Because when you complement it, De Morgan's law applies. Okay. Now coming to A greater than B. A greater than B. So A greater than B, the first expression was A3, sorry, A3 B3 bar plus X3 multiplied by A2 B2 bar. I'll quickly explain where is that. Please note that these are art and it goes on like this. Okay. So let me erase the already highlighted parts. Okay. So what is this line? I'm first I should get A3 B3 bar, right? So where is A3 B3 bar? I'm having A3 B3 bar here. So that line comes here. Okay, so that line comes here. And at the same time, that line comes here also. Here also. Sorry, A3 B3 bar, right? This is A3 bar B3. So A3 B3 bar, this line comes here. Okay, I'll repeat. I think I made a mistake. So we need A3 B3 bar. A3 B3 bar is here. So this line here comes as an input of my OR gate, which is A greater than B. My next input here will have AND the operation of X3 A2 B2 bar. Now what is X3 here? This is your X3 output. So X3 is ANDed here with A2 B2 bar. So this is what is your A2 B2 bar is. So A2 B2 bar ANDed and that is my another input of my OR gate. So likewise, I will get, so there will be a three connection here. This will be X2, sorry, this will be X3 and then X2 multiplied by A1 B1 bar. And you will have a 4 input combinations for this AND gate going to this OR gate. So likewise, you implement this combinational circuit. Now, if you want to represent this as a block diagram, so what will be how will be the block diagram will look like? So what are its input and output ports? So this is a complete block here. This is how your complete block will look like. Forget about whatever it's inside. So what are your input and output ports? A3, B3, A2, B2, A1, B1, A0, B0 are your inputs. A greater than B, A less than B, and A equal to B will be your outputs. So a block diagram representation of a 4-bit comparator simply will look like this one. As an example, if you look, if A is 0, 1, 1, 0 and B is 1, 0, 1, 0, you will get first A3 and B3 are compared here. So A3 and B3 are compared. B3 is greater. So B is greater than A, which means that A is less than B. This will, your output across this particular line will get triggered. Any doubt? Okay. Next, we move on to the delay calculations. Delay calculation is very, very important in identifying for any special digital designers, because if you do not know at what time your input will come to your gate, then it is very hard for you to design your subsequent shell circuits. So in general, let us consider that you are having a logic gate here. All right. So this is a logic gate. Some combination. This can be a comparator, a multiplier, adder, divisor. Any gate it can be. And we are having, say, n number of inputs here. So I'm having one input here, second input. Likewise, n number of inputs I'm having. We can always not be sure that all my inputs will be available at the same time. How can I verify that? If you look at even a full adder circuit, if you let me take some, yeah, even if you take this particular circuit, what is this particular circuit? This is some code converter circuit. If you look at the inputs at this particular point here, there are two inputs. The arrival of this input and the arrival of this input will be different. The arrival of this input might be quicker because it is only through one NOT gate and a AND gate, whereas this particular input might take longer time because or this might be shorter also, right? So because there is one input coming here, one through a NOT gate, one through an OR gate, and then one through again a NOT gate. So which means that the input arriving across this terminal, this line and across this particular line, they will be different. So which means that the at what time will I have my output? I will have my output across. So I can always represent the output time across this output terminal as maximum time taken for out of T1, T2 till Tn. Whatever is the maximum time that input is taking, that max of that particular timings plus the logic gate timing. Inside this logic gate, it might take some T seconds, right? So that particular time. So I can always represent it this way. So for your sake of understanding, say let us assume I have represented here, but maybe a larger diagram. I'm having an AND gate. One input is coming at say 1 nanosecond and another input is coming at 3 nanoseconds. This gate delay has got its own delay of say 1 nanosecond. So first, what is max of this 1 nanosecond and 3 nanoseconds? Max of 1 nanosecond and 3 nanosecond is 3 nanosecond plus the gate delay, which is 1 nanosecond plus 1 nanosecond, which is equal to 4 nanoseconds. So you will get your output only at 4 nanoseconds only. Okay, so this is the same logic that has been implemented here. So let us consider a full adder circuit. Okay, so then we will assume how to calculate delays. So consider a full adder circuit where all the inputs are available at time 0. So the beauty that is here is all the inputs are given here at all the inputs here are available at time 0. This is available at time 0. Okay. And what they have given here is each gate, assume that each gate has got a delay time of t seconds. So hence this will have a delay time of t, this will have a delay time of t, and this gate will have a delay time of t. All the gates will have a delay time of t. So first let us see at what time you will have sum and what time you will have carry. So what will be the, when will you have the output? What is max of 0 and 0? It is 0. So 0 plus time t seconds is 0, max of 0 plus 0, 0 comma 0 plus the gate delay time will be equal to t, right? So which is what is written here. Okay. Now at this AND gate also is the same, max of 0 comma 0 plus the gate time. So your output will be across this AND gate will be at time t nanoseconds, t seconds let us take. So this 0 here is available at 0 time. So this is available at 0 time. If this is available at 0 time, what will be the output here? What is max of 0 comma t plus the gate time t? Max of 0 comma t is maximum plus the gate time t, which will be 2 times t. So this output here will be available at 2 times t. So sum is available at 2 times t. Now let us look at carry. So here it is available at 0. So hence it is available at 0. This is available at t, hence this is available at t. What is max of 0 comma t? It is t. T plus the gate delay time t is 2t. So this is at 2t. And this is already at t here. So what is max of t and 2t? Which is the maximum, t or 2t? 2t is maximum. So 2t plus the gate delay time t will be equal to 3t, which means that your carry will come only after 3 time seconds when compared to the 2 time seconds of your sum. So carry will always come late. Okay. So this is how you will calculate the delay timings of any gates. Similarly, you can perform the delay calculations of 4-bit parallel adders also. So when you are performing for a 4-bit adder, let us do the delay calculations now. I'll show you how to calculate it. This is a ripple carry adder, right? Why ripple carry adder? Because this carry have to propagate from one stage to the other, and this S4 can be calculated only if C4 is available. This S3 can be calculated only if C3 is available. S2 can be calculated only if C2 is available, and S1 can be calculated. Obviously, all three inputs will be available at the same time. Okay. So now look at this will be available only after 3 time seconds, whereas your sum will be available across 2 time seconds. This will be this will be available across 2 time seconds. So likewise, you have this carry there will be an increase in the time. How do you calculate it? Let us go step by step to calculate the time seconds. I'm going to take a general block. Okay, so instead of one single block, let me take a general block, and I'm going to assume that my x is available at 0 time, y is available at 0 time, and my carry is available at m times 3. And the next stage for this full adder FAI, my sum SI will be available after 2 time seconds, and CI plus 1 will be available across 3 time seconds as in the previous example. So XI and YI are stable at 0 time seconds, while CI is available, assumed to be stable at m times t seconds. Now let us again go back to the full adder circuit and substitute here. So this is available at 0, this is available at 0, this is available mt. What is max of 0 comma 0? It is 0 plus t, so this is t. Again this is t, right? Max of 0 comma 0 plus t. So hence t, so t is there. Now at this particular time, here it is mt. Okay. Now what is max of t comma mt? It is going to be mt, right? It depends on the value of m. It depends on the stage actually, plus the gate delay t. Now at this particular time, it is max of t comma mt plus t. So if you compare this t with this max here, then it will be max of t comma mt plus t comma this particular t plus this time second. So which means it is max of t comma mt plus 2t. Now let us calculate. So we have got a generalized expression. Let us calculate. When I is 1, meaning when I is 1 means the first carry, your m will be 0 because we are giving all the inputs at the same time. So m is 0. So your S1 here, just to substitute for m equal to 0. What will happen? You will have max of t comma, if m is 0, mt is 0 plus t, max of t is t, t plus t is 2t. So your sum is 2t here. Similarly here, max of t is t, t plus 2t is 3t. Now when I is equal to 2 means you are propagating to the next stage. And what will be the value of m? M value will come because of the carry, right? Your carry C2 will come only after 3 time seconds. So m value will be 3. Now if you substitute t comma 3t means this will be 3t plus t. So your sum will be available at 4t. Here it is 3t plus 5t, sorry, 2t will be equal to 5t. So it is 4t and 5t for sum and carry. Similarly, when I is equal to 3, this m value will take from the previous carry stage 5. So this continues. Sum will be 60, carry will be 70. And for the fourth stage, m is 7, sum is 80 and C5 is 90. So you can keep on continuing it. If you want to generalize it, then obviously from the expression itself, you can find out, right? What is S1? Sn, in fact, Sn will be equal to 2 times the number of stage. That is, if I is equal to 4, it is 4 multiplied by 2 is 8, which is 2n times t. Now what will be the carry? It is 2n plus 1 will be, right? So 4 and 9 here. So your carry Cn will be equal to 4 2s are 8. So 2n plus 1 times t. Okay. So there has been slightly a generalized method has been written. So both are same. Okay. So 2nt and 2n plus 1t. So which means that your carry will take longer time to propagate. So propagation delay of a ripple carry adders, they are proportional to the number of bits. If you are going for a 64 bit, so look at the time. If you are using 64 bits, so you will have 64 plus 165 stages. So 64, 128, 129, 129 time delays it will take. Okay, so that is how the delay, the maximum delay that you can come across will be n minus 1 times 2 plus 3t will be the maximum delay that you will come across. Okay, let's take a simple NAND gate just for the sake of understanding. If you have a 2-level NAND gate, if each NAND gate is producing you an 8 nanosecond delay, this is also 8 nanosecond delay, then your output will be available across 16 nanoseconds delay. There is a purpose in telling you this because when we implement a complete comparator circuit, ripple carry adder circuit or carry look ahead circuit, which is another part of a adder circuit, we will be using these delay calculations. So if you want to design faster circuits, there are 3 different ways. Either you can use ECL technology than TTL technology. What is this ECL? ECL is nothing but the electron control logic, the emitter collector logic. Okay. TTL is transistor logic. Okay. Uh, so you have to use either a better technology. Obviously, the faster technologies will be more expensive and it will require huge amount of power also, but you can achieve a lower levels of integrations. And then you have to simplify your gate levels to just 2 levels only. 2 levels in the sense your input level and your output level. In most of the circuits, if you look, so this is a 2-level logic. So your inputs are coming to the first level and that first level is processed and it is processed for the output stage. If you look at this circuit, again, this is a 3-level circuit because this is one level, this is second level, and this is third level. Okay. So likewise, you have to let us see what about this. This is a multi-level circuit. Okay, multiple stages are here. So so that is what is a 2-level logic circuit is. So you have to implement 2-level logic circuits, and which is the better way to implement a 2-level logic is either convert it to an SOP or an POS form, then it will become a 2-level logic circuit. So when you are implementing a 2-level logic circuit, obviously the circuit design will be complicated. It will become a very, very large circuit. You will have huge number of inputs, and the better way is you have to look ahead the techniques. There will be additional costs, obviously. You have to apply for look ahead techniques. What is a look ahead technique is you have to your circuit must predict what kind of inputs are going to come and what can be the possible outputs. So that is what is called as the look ahead technique is. So any doubt here till this? Okay, good. So now every time whenever we were discussing the carry, we have been always telling that triple carry adder is hugely disadvantageous for the reason your output must wait for the carry output from the previous stage, right? So carry input for that particular stage to the from the previous stage. So this is what is again written here, which is the huge disadvantage of a ripple carry adders. So a ripple carry adder here, they are very, very slow for the reason your A3, B3 outputs, they will be available only after C2 is available. And till that particular time, till your C2 is available, your output across C3 will have some random or incorrect outputs. Okay. So similarly, your C2 has to wait for C1 and C1 has to wait for C0 and etc. Right. So you could recall the full adder stages. So thus C3 and S3, you will get the final output only after everything has settled down. Only every output has come to a stable state. Or in other words, only after all carry has rippled from the first stage to the last stage. Only then you will get this C3 and S3. C3 means carry out the last stage and sum out of the last stage. So how do we solve this problem? How do we solve this problem is we are going to look ahead our carry, as the name implies. We are going to look ahead of the carry that we are going to generate. So this particular generator that we are going to design, which will generate your carry well in advance, is called as a carry look ahead generator. Okay. So we are going to design this carry look ahead generator. I think we will start from next class again. This is again a very long and a lengthy part here. So we will cover it in the next class. Okay. Because this again requires a fresh mind to understand. All right. So I think we will stop here. Ideally, um, your mid-semester portion must be till carry look ahead uh, generators. So this is what we are going to generate for a full carry. So the IC. So normally I have taken this course for the past 2-3 years now. Normally I will complete with this look ahead carry for your mid-semester exam, but we are very late. At least we are late by 4 classes. Okay, that is because of the online mode. Uh, if it is in a physical mode from your faces, I can understand whether you understood or not, and we can quickly move. But here your response has been very great, so hence it is slightly delayed. Okay, so we will continue this. I mean, only this is the only and the last uh, a kind of a theoretical part, slightly boring. I should not say boring, but slightly hard to understand, and so that is the circuit. One, this will be the last part. After that, again, you can enjoy with the decoders and encoders, and then you will have flip-flops, counters. Beautiful circuits are yet to come. Okay, so we will continue this in the next class. Any doubt, you can stay, else you can leave the class.